Hello everyone. Thanks for joining the presentation for our ICPP 2020 paper with the title Deep Reinforcement Learning-Based, Elasticity-Compatible, Heterogeneous Resource Management for Time-Critical Computing. My name is Zixia. This paper is written by me and Dr. Liqiang Wang from University of Central Florida and Dr. Gang Quan from Florida International University. Firstly, we would like to briefly talk about the background of this work. Nowadays, the amount of data analytical works is increasing every day, and some of them are also time-critical. They all call for larger-scale computing resources, and the multi-cluster computing environment shows its benefit and the necessity as an option to expand the computing resource. We listed some examples of such environment and also provide an illustration of a multi-cluster environment. To use such environment well, we do need an efficient resource management approach. However, there are many features to consider, including computing system features and job features. Especially clusters forming the environment can be heterogeneous and may be elastic. Other approaches, such as rule-based ones, can have difficulty in considering all of these features. Therefore, what represents a deep reinforcement learning-based resource management for such environment. Now we'll provide the main contributions of this work. We propose a deep reinforcement learning-based approach utilizing LSTM model and also multi-target regression with partial model sharing mechanism. We also compare its effectiveness with multiple baselines. This approach is designed for distributed multi-cluster computing environments with considering its heterogeneity and also being elasticity compatible. It provides scheduling support for time-critical computing in such a multi-cluster environment. Now we state the problem description. As shown on the left, the system receives data analytical jobs from users. These jobs can be of multiple categories, such as they can be streaming jobs that are intrinsically time-critical and do repeating executions on batches of data. There can be some other time-critical jobs that will be executing only once, or can be other general jobs. Such workload of jobs gradually arrives, and our resource management should make good decisions by sending a job to one of the clusters in the environment for their computing demand. Each cluster in the environment represents its overall computing resource as a number of executors, and executors among different clusters can be heterogeneous, such that the computing capability of them are different. Some clusters may also be elastic, that is, their executor numbers can be temporarily expanded with an upper bound when necessary to fit workload pressure. When the job executes on the designated cluster, it will require some number of executors based on its feature. We set two goals for the resource management. First, to reduce occurrences of missing temporal deadline events of all jobs, and second, to maintain a low average execution time ratio for such a hybrid workload with multiple time-critical and general jobs. After introducing the problem, we now begin to talk about our deep reinforcement learning-based approach. But firstly, we would like to give a brief introduction of reinforcement learning. Roughly speaking, it is based on several concepts such as the environment, a state at some moment, an episode, which is a round of game that marks the reaching of the termination state, the set of actions, the action reward, and the value of action, which focus on the accumulated rewarding in a longer duration. At moment t, the model takes an action based on the state, observing the feedback, and consider it as an experience. From experiences, we could update the model towards taking better rewarding actions. Specifically in this work, we are using reinforcement learning on deep neural networks in hope of better extracting in-depth connection between state and actions. The deep neural networks are used as action value estimators that can guide the resource management. Now we introduce our approach. The environment here is the entire computer system. The action set when scheduling a job contains number of actions equaling to the number of clusters in the environment. An episode is the whole process of scheduling and finishing execution of a workload of jobs. But we still have some challenges as listed. We start with answering the state. For state, we let it contain two components, computer system information, and job information. We list the state on the right. For each cluster, we have representations such as for its normal capacity and maximum capacity if elastic. We have cluster heterogeneity factor. This is a number to represent the computing capability of executors in that cluster. The higher, the stronger. We also have its occupation status in some past time steps. This will be traversed to a 150 size vector, and we'll discuss it later. For the job, we have features such as its expected heterogeneity factor, which is also used to measure its standard execution time. We have its heterogeneity sensitivity measure, which, roughly speaking, tells us a range of heterogeneity factors, that when cluster heterogeneity factor is in this range, the job's execution time in cluster will be proportionally affected from its standard execution time by the cluster heterogeneity factor. We also have a discrete resource request distribution that tells the possibility of a streaming job requiring certain number of executors in one of its repetitive executions, possibly due to data amount fluctuation. You may refer to our paper for more explanations about the definition of the state in our problem. To evaluate an action taken, we choose to define its value in long term, since instantaneous reward for an action in our problem, which is deploying a job to a cluster at some moment, is hard to define due to many long-term effects of an action to the system which naturally exist in our problem. We also want to attend to several things when defining the action value. We'll list them here as value definition ideas. With such ideas, we define the action value as follows, and we provide explanations for the parameters. More explanations for the formula are in the paper. Two things to note here. First, a job can have more than one missing deadline events, since streaming job can do repetitive executions with different batches of data. Second, weighted factors can apply to components of the value for balancing. We omit is showing here in the formula. We now provide some brief interpretation for the value definition. Firstly, both missing deadlines and execution delay ratio are considered in the definition. Second, missing deadlines of other jobs may affect this action value, so mutual influence is attended. Third, missing deadlines with resource weighting at their execution beginning are decayed over number of newly arrived jobs after the action, in purpose of distinguishing influence of different jobs on resource computation. Yet other missing deadlines without resource weighting will not be decayed. Influences of heterogeneity is considered explicitly for missing deadlines and implicitly for execution delay ratio. Influences of elasticity is also considered implicitly in the formula. In this slide, we talk about our model structure. We notice that there are some temporal information in system state, so we want to utilize LSTM, which is more specialized for such temporal sequential information. Also, we use neural network as action value estimator and would like to choose action with max value. So how to better estimate value is important to us. Note that the value definition contains multiple components for different factors affecting action value, but also make it more difficult for prediction. Therefore, we'll consider treating different components of the value as multi-objectives in reinforcement learning and use multiple neural networks as value estimators for all components and combine their results as the overall action value estimation. This can be seen as a multi-target regression problem. For those networks, we let them share a few layers in front for a joint input feature extraction structure, and each network still has their individual layers in the end for their differentiated outputs. We provide the overall network structure on the left and 3 value components on the right. Each corresponds to the estimation target of the network on the left. Note that 3 value components together can form the value definition we provided in the previous page. We also used some training skills in our approach. For the status traverse, The purpose is to convert the original cluster occupation status vector into a series of segments which may reveal occupation evolution by each segment available to the LSTM cell, while preserving the original temporal information which can be utilized by LSTM structure. Figure on the right shows such process for one of the clusters. It will convert the original status vector for the cluster into a length 150 vector. For training with decayed learning rate, we hope this can assist in getting more swift model change in the early stage and finer adjustment in the later stage of the training. We also adopted some skills in our previous publication as reference 12, including training with randomized workload, modified epsilon gradient exploration, and a skill for letting the approach also selects a job during making scheduling decision when there are multiple jobs awaiting scheduling. This could cope with the situation if multiple jobs exist in the global job buffer, which holds all jobs before deployment to the cluster. As the last slide of our approach, we provide our training architecture in an episode. Firstly, our job generation module gradually generates jobs in different categories for the workload during the episode based on the statistical job arriving pattern and then sends them to the global job buffer. When the job buffer is non-empty, the query engine queries our deep neural network for action values of each job and selects a job and its action with max value in the global job buffer. This job will then be deployed to the designated cluster for execution, and this scheduling knowledge as an experience is recorded in the knowledge replay buffer. Meanwhile, our multi-cluster simulation engine simulates the execution of the computing environment in an episode and records some performance metrics. At the end of the episode, these performance metrics will be calculated into the observed values for recording actions and supplement to the knowledge replay buffer. If enough knowledge has been collected so far in the training, the reinforcement learning will randomly retrieve some knowledges from the replay buffer and provide an update to the model, which could be used in the next episode. Now we begin to talk about experiment results. The experiment is done via simulation with a testing environment of 5 clusters. Clusters in this environment are heterogeneous and 2 of them have elasticity as well. We use a separate elasticity controller for regulating cluster elasticity behavior and a generic local intra-cluster scheduler for intra-cluster job executions. Note that our approach has the potential to coordinate with different elasticity controllers and local schedulers. To compare with our approach, we use 3 rule-based baselines, random, round-robin, and MAF, where the last baseline roughly mimics the idea of the best baseline in reference 12 of the paper. Additionally, we compare with another reinforcement learning approach denoted as RLFC, which roughly follows the approach in reference 12 as well. For job arriving patterns, 3 are used, including uniform, Bernoulli, and beta. Instead of training a model for each pattern, we only train a model for uniform and show its generality by directly use it on the other 2 patterns. For performance metrics, we use TMDL and AJER relating to the 2 goals of our resource management. Further, we define S-log as an integrated score attending to comprehensive performance in both goals. In this figure, we show comparison of our approach and baselines in different training episodes. For S-log score, the higher the better. For each vertical comparison, all models are included to compare for 50 testing episodes. The same workload is used for all models in one testing episode, but is regenerated for each testing episode. From it, we can see that MAF performs the best among baselines, and our model gradually improves itself during training and surpasses all baselines during the mid of overall episodes, and continues to increase its performance towards the end of the training. A detailed performance comparison between our final model after training and MAF is shown in these figures, where data is sorted by one metric for viewing convenience, and the statistics are shown in the table. We can see that our approach outperforms MAF in a large scale. It reduces TMDL by 5.57 times and AJER by 2.92%. We also show what we call the FSN distribution for our approach in 50 testing episodes. It also shows good performance. During experiment, we notice a phenomenon that our model can perform equivalently well or even better for workloads that is statistically less stressful than the ones in training. For uniform pattern, this can be changed by its parameter b. When b is larger, the workload can becomes less stressful. For this experiment, b is 33. In the next slide, we show the model performance when b becomes larger. In this slide, for finger A to C, we are showing a stress-reduced workload with b equals 36, and in finger D to F, we are showing a more stress-reduced workload with b equals 40. Indeed, as workload becomes less stressful, our approach performs even better. This can be observed in all performance metrics. Since the stress of the computing environment could largely vary in daily usage, the generality of our model to fit for such variation is certainly an apparent advantage. As stated previously, we also want to directly utilize the obtained model via training with uniform pattern onto other two job arriving patterns, Bernoulli and Beta. Results are shown in this slide. The results show that it can work well directly with other two job arriving patterns. This may be because the obtained model is capable to capture intrinsic information from the system status and is less sensitive to job arriving pattern shift. This observed irrelevancy of job arriving patterns in experiments is a great supplement towards approach generality. Now we compare our model with another reinforcement learning model with fully connected layers named as RLFC. In this comparison, we additionally add another model variant also obtained by our approach, but with a slightly different balancing between multiple objectives of the reinforcement learning. We called it RLSFCB. So in the table, both models with stars are models by our approach. In this slide, we put these three models and MAF together into 50 testing episodes. We can see that although the FC model achieves slightly better TMDL than our LSFC, but it pays a too large cost in AJER and thus has lower score in S-log than both of our models. So the FC model in experiment shows a weaker overall performance. Meanwhile, LSFCB could surpass the FC model in all aspects, but its balancing in objectives causes a hit in the S-log score comparing to the LSFC and promotes the LSFC model as the best performing model here. The good thing is our approach grants the freedom to choose either of our two models per user preference. After seeing the good performance of our model, we want to further explore its behavior, so we show job scheduling sequence in one episode. From finger A to B, our model really has a very different scheduling pattern comparing to MAF. In brief, our model tends to utilize clusters with larger capacities and larger heterogeneity factors more during the early stage of the episode when computing pressure is not peaked, in favor of better performance in both goals. But when pressure rises, it can well utilize all cluster resources for overall performance. Also, other figures show that our model can provide differentiated scheduling patterns for jobs in different categories, such as for streaming jobs, which is category 1, it seems to prioritize clusters with stronger computing capability and with elasticity, presumably to fit streaming jobs' fluctuated resource requests. Figures in this slide is another way to illustrate the differentiated job categorical scheduling patterns for our model. From them, we can see that such difference is apparent. And this finishes our experiment section. In the last slide, we give our conclusion. In this work, we obtained an elasticity-compatible resource management via deep reinforcement learning for heterogeneous multi-cluster environment. Comparing to the best baseline, it reduces the occurrences of missing deadline events for workloads of 1,000 jobs by around 5 times to 18 times, and reduces average execution time ratio by around 2% to 5%. It also shows better performance than a previous reinforcement learning-based approach with fully connected layers. This is the end of our presentation. Thanks for watching.